Okay, welcome everybody. This is a joint CGD CISL seminar, and I'm happy to see people from both labs here. Today's speaker is Dr. Yang Song. She's a postdoctoral fellow at King Abdullah University of Science and Technology, that's KAUST, in Saudi Arabia. She's affiliated with the Spatial Temporal Statistics and Data Science Research Group, led by Professor Mark Genton. She received her PhD degree in statistics from Renmin University of China in 2023. During her doctoral studies, she took research visits to Hong Kong Baptist University and KAUST, and she received her bachelor's degree in statistics from Beijing Institute of Technology in 2018. Her research interests include spatial temporal statistics, subsampling methods, non-parametric statistics, computational statistics, and high-performance computing with applications in climate and environmental sciences. And she was part of the team that won the 2024 Gordon Bell Prize at Supercomputing for Climate Modeling, largely thanks to her scalable climate model emulator. So we're happy to have you here today. And there's one more slot left if you want to meet with her this afternoon. You should have got an email with the link. So,
thank you, Alison. And hello, everyone. I'm pleased to share you with my research on efficient stochastic generators with spherical harmonic transformation for high-resolution global climate simulations from CISL 2. This is a joint work with Professor Zubair Khalid and Professor Mark Genton. So climate change is evident in rising temperatures and sea levels, extreme weather events. And here we can see a global climate report in August 2024 provided by the NOAA, and we can which present the selected significant climate anomalies and events. And we can see that the pink thermometer labels the regions where the average temperature in August is higher than the previous years, ranking among the top. And we can also see this blue mountain labels the regions with reduced sea ice extent. We can also see the heavy rains and typhoons. So climate change poses significant risks and requires comprehensive research and immediate action. So the Earth system models, or the ESMs, are very important in climate science. They are actually some complex mathematical formulations like the PDEs that can describe the Earth's climate system. They are developed based on the foundational principles of physics, fluid dynamics, and chemistry. Using the ESMs, we can generate climate simulations at even kilometer scale spatial resolution, which can serve as the supplement to the real-world data and help us to understand the climate change, to predict the future trajectories, and to make policies. But when we use the ESMs to generate multiple ensembles of the climate simulations, we will meet challenges. We will have the computational demands. So, for example, for the Goddard Institute for Space Studies, the GISS, they required over 100 million CPU hours on their supercomputer to generate 147 terabytes of the simulation data. So we can also see even the generation process will be time-consuming even with the support of the supercomputer. And after the generation, the output, if we want to store or to manage the output, we also need some advanced hardware and software. So it's unaffordable for most individuals and institutes. And we will have the financial constraints. So from the perspective of statistician, we find a solution is to provide a practical complement to an ESM to build a stochastic generator, or the SG. So the stochastic generator is actually a statistical model trained on only several ensembles of the climate simulations. And then they can be used to generate fast stochastic approximations for the simulations. We call them emulations. So we hope the emulations can be statistically consistent with climate simulations. And instead of storing all the output, all the climate simulations, we only need to store the model parameters in the climate in the stochastic generators, so that whenever when we want to use the data, we can generate using our stochastic generator. So here I provide some reference where we can find the applications or the development of the stochastic generator. And here we can see the table which summarizes the difference between the stochastic generators and ESMs. So actually, the stochastic generators will use climate simulations as the input, and we will build a statistical model and generate emulations and only store the model parameters. Okay, so in our work, we will build a stochastic generator for the surface temperature simulations from the CESM toolines 2. So we can find the CESM toolines 2 in this website, and it includes a wide range of physics and ecosystem variables. For each variable, we have 100 independent ensembles at about 1 longitude-latitude spatial resolution, covering the period from 1950 to 21,000. But in our work, we will only focus on the surface temperature. So we use YTR capital Li, Lj to represent the surface temperature at the R's ensemble, the latitude capital Li, longitude Lj, and the time point T after 2014. So the number of ensemble, the capital R equals 7, so we will use 7 ensembles. The number of latitude and longitudes, the capital I and capital J depends on the spatial resolution. And the number of time point, the capital T, that relies on the temporal resolution. So here we consider the annual, monthly, and daily data. And we will see we need to store about 5 million, 60 million, and about 2 billion data points for each ensemble of these simulations. Okay. So before we build the stochastic generator, before we build the statistical model, we need to know what our data will look like. We need to see the characteristics of the data so that we can use proper tools to model the data, to model the characteristic of the data properly. So in plot A and B, we show the ensemble mean and ensemble standard deviation of the annual climate simulations at a fixed time point. So we can see the color in plot A represent the surface temperature in Celsius. So it makes sense because the closer to the equator, the higher the surface temperature. And we can also see near the Himalaya and Andes region, the surface temperature is lower than the surrounding regions. And for the standard deviation, you can see near the 2 poles, we will have higher uncertainty, higher variability, and as well as the region near the equator is because of the El Nino. And now we fix 2 grid points, one on land and one on ocean. We call it GL and GO. We want to show the time series on these 2 grid points. So in plot C, we show the annual time series at GO and GL. So we see different colors. So different colors represent the data from different ensembles, and they share a common trend. And we can see a black curve in the middle, which represents the ensemble mean. And this curve represents the radiative forcing, which is an influential factor for the surface temperature and is related to the greenhouse gas emission, and it's also for the time series on the grid point on the land, GL. So in plot D, we show the monthly time series at these two grid points. And if we compare the data, the time series in plot D with those in plot C, you can see the interannual cycle. So for the monthly and daily data, we also need to model this kind of seasonality in the data. And as we saw before, all the ensembles will share a common twin, but they have their own shape. And the data online will have higher variability, higher uncertainties. So this may indicate some non-stationarity between line and ocean. So now we take a look at the distribution of this time series at these two grid points. The first row is for the GL, the second row is for GO, and we can see the histogram of the time series at different temporal resolution, annual, monthly, and daily. So we can see we also calculate the skewness and kurtosis of this distribution. And we can see with the increase of the temporal resolution, you can see the data is no more Gaussian. So we have a skewness as well as the heavy tails. So it means for the data with higher temporal resolution, we also need to Gaussianize the data or somehow to remove this kind of skewness and kurtosis. So this plot also shows the skewness and kurtosis for all the grid points. So still, the darker the color in both red and blue for the skewness, the more skew the data. And for the kurtosis, the more red, the heavier the data's tail. So you can see we need additional techniques to Gaussianize the data for these two temporal resolutions. Okay, so we have seen the data characteristics, like the data is large, so we may have the challenges when we model the data because of the computational limitations. And the data located over the globe, which means methods based on the assumption of stationary or isotropy will be not, the methods based on the Euclidean distance may be not that proper. And we see the non-stationary spatial structures, like the non-stationarity between line and ocean, and we will see another kind of non-stationarity later. And we see non-Gaussian temporal trajectories. So based on these data characteristics, we will use various techniques in our model to capture the characteristics of the data better. So the first step of the modeling is to decouple the data. So still we have surface temperature Y at time point T, ensemble R, and grid point capital Li, Lj, and we have a common twin, remember that. So it will be shared by all the ensembles. So in our model, we need to show this. So we will decouple the data into deterministic and stochastic components, which are marked by in blue and red colors. So for each grid point, like we can see that our time series will be decoupled into the common twin MT and the standard deviation sigma, and as well as the stochastic components, which is different for each ensemble. But this deterministic components is shared by all the ensembles. And we will follow the literature to use a two-stage approach. That means we will first assume the independence of the data, and we model the deterministic components first, remove them, and then we focus on the stochastic components. We will model the stochastic components using the stochastic models or stochastic process. That's the general idea. So we begin from the deterministic component. We will use an infinite distributed like model. So for each grid point, we will have the function mt, the common trend. Remember, like the ensemble mean, the common trend shared by all the ensembles. And here in the model, we have xt. Xt represent the radiative forcing, which can influence the surface temperature as we saw before in the plot C. And we assume the common trend will rely on the current radiative forcing xt by slope beta 1, as well as the past radiative forcing xt minus s, the s start from 1 to infinite, and by the parameter beta 2, by the slope beta 2. And we can see the impact of the past radiative forcing will decrease exponentially with the year. That's the idea. And so now we have this model, and we will estimate the parameters beta 0, beta 1, beta 2, rho, as well as the standard deviation sigma using the maximum likelihood method. But this is only for the annual case, it's the simplest case. Remember that for the daily and monthly case, we have interannual cycle. So we need additional harmonic terms to account for this seasonality. So like, for example, if we model the deterministic component of the daily data, the t will represent the tth year, the tth day. So this number will represent the number of year. So from here to here, the model is as the same as the annual case. But remember, we need to include the harmonic terms to account for the seasonality. So we will have additional Tukey terms to model that. And here, the higher the k value, the larger the k value, the higher the frequency these harmonic terms can capture. So the capital K for daily case will be greater than the capital K for the monthly case. That's the idea. And finally, we will store these parameters for each grid points. That's the modeling of the deterministic component. So after the modeling, we just remove the deterministic component and focus on the stochastic component. So now we have capital Z, T, R, capital L, I, L, J to represent the stochastic component at time point T in ensemble R and grid point capital L, I, L, J. We need to model that. So if we fixed at time point T and ensemble R, we will have a data, we will have a spatial data. The number of location is capital IJ, is about 55,000, so it's huge. If we want to model this spatial data using Gaussian process or something, it will be time consuming. So there are many methods in spatial statistics to solve this problem, which is called the big N problem. So here we will only use the low-rank approximation methods because it will not assume too much because our data is very complicated. So we try to avoid to assume the isotropy or the non-stationarity to just use some simple assumptions. So here, the low-rank approximation is actually we represent the data by a linear combination of basis functions H alpha associated with their coefficients. Is also indexed by alpha. So we have capital A basis functions. Sorry, this alpha should begin from 1 to capital A. And these basis functions are known. So finally, we don't need to model the data here. You just need to model their coefficients. And if the number of capital A is much smaller than the number of locations, we just reduce the computational limitations. So the key point is how to choose the basis functions. In literature, they will give some specific form and to tune the parameters in these basis functions so that the basis function can be multi-resolutional and can capture different scales of the data. So it's actually it's hard to, we need to tune the parameters in this basis function. But in our case, remember that we are modeling data, we are modeling the global data. So here we use spherical harmonics, this capital HQM. We can just take the Q and M to be the index, like the alpha. So the spherical harmonics HQM means the HQM means the spherical harmonics at degree Q and order M. And it has closed form. You can see here we have latitude, longitude, and it transformed to be the point on the sphere. And from the last term, we can see actually the spherical harmonics, they are complex valued function. So in real application, we may use this spherical harmonics to model complex valued signals or function. But in our case, we just focus on the real valued functions. So actually, we can find a set of real valued spherical harmonics by some simple linear transformations. And the spherical harmonics are also normal to each other. So if we the basis with degree smaller than capital Q will span a Q square dimension space. Why Q square? Because the index Q, the degree Q, will vary from 0 to capital Q minus 1, and the order M will vary from minus Q to Q. So that's why it's Q square. And actually, this spherical harmonic transformation is that we project the data to a lower dimensional space of Q square. And we have the residual term, which capture the remaining informations is the residual term. We will also assume it follow a normal distribution. So if we want to understand this SHT, the spherical harmonic transformation, in an easier way, then we can think it as a spherical version of the Fourier transform. So we know Fourier transform, and this is like a Fourier transform for the data on sphere. So that means we just transform the data in space to the coefficients in spectral. So it will be easier to understand this SHT. So here are two plots to show this SHT. So like in plot A, we have the stochastic component at the 9th year, and the first ensemble is in the spatial domain. And after the SHT, we get the coefficients, which indexed by degree Q, begin from 0, and order M, which varies from minus Q to Q. So it looks in this shape. And this plot shows the log of the norm of the coefficients. So the norm of the coefficients represent the energy at this Q and M, at this frequency. So the lower the frequency, the larger the energy. So with the increase of the degree, or with the increase of the frequency, the energy also decreases. And the decay rate actually reflects the smoothness of the data. So when we model it, we will choose a capital Q between 0 and this 144, so that we can capture the main characteristics of the data, but remove the noise. That's the idea. So for the number of spherical harmonics, or the capital Q, the maximum value of capital Q depends on the spatial resolution, and in our case is 144, like what I showed here. So we will choose a capital Q smaller than the Q max. So how this capital Q influence the performance of SHT, we can see here. So in plot A and B, we show the absolute value of the residual under different Q values. So with the increase of Q, we will have a better approximation, or we can capture more details of the data. But it will also increase the computational complexity. So the Q actually trades off the approximation quality against the computational complexity. Okay. So we summarize the advantages of using spherical harmonics. So they are actually natural basis functions for global data. And they are easily available because they have closed form, and they are multi-resolution basis functions. So we don't need to tune the parameters in the basis functions. We just need to find the proper Q. And also both the SHT and the inverse SHT can be efficiently calculated with at most the order of Q cube computational complexity. That's the advantages of the spherical harmonics. Okay. So after we transform the data from spatial to the spectral domain, we can model the data or the coefficients in the spectral domain. So here we have coefficients at each time point and ensemble R. We order them in this order, and we put them all together and form a vector, coefficient vector, the bold S. We will model the spectral dependence, like the dependence between different coefficients, which means the spectral dependence, and the temporal dependence of these coefficients. Like in the spectral domain, we will build a stochastic model for these coefficients. But this model will rely on the characteristics of the data. For example, we say we have non-stationarity in spatial domain. Like if we see here, can see at each latitude, we can assume stationarity of the stochastic component. But if we see at different latitudes, can see different spatial structures. So we need to make an assumption of axial symmetry, which means we will assume non-stationarity among the latitudes, or only data on the same latitudes are stationary. So if we want to calculate the covariance or the correlation of the data or of the stochastic component at two grid points, the capital Li, Lj, and the capital Li prime, Lj prime, then this correlation will only depend on their latitudes and the distance between their longitudes. Okay. So under this axial symmetry assumption, the covariance matrix of the coefficients vector will be a sparse matrix with this number of non-zero elements, and we know where these non-zero elements are. Like we will only assume dependence between the coefficients which have the same order, the same M. Yeah, so that's the covariance matrix of the coefficients. And also we observe non-stationarity among land and ocean. So we will give different Q values for data on land and for data on ocean when we do the SHT. So we use QL for data on land, QO for data on ocean.
Ask a question, please.
Yeah, please.
What do you mean by stationary? A time concept.
It's a spatial concept.
So what does stationary mean and
the stationarity means that if we calculate the covariance of the data on two grid points, this covariance will only depend on the distance of these 2 points. Will not depend on their exact location. Only depends on their distance. So the axial symmetry is we only assume stationarity among each on the same latitude, means the covariance will depend on the distance of the longitude, but the latitudes of the grid points. That okay? Okay. Yeah, thank you. Okay, so now is how we model the spectral dependence of the coefficients. And then we model the temporal dependence of the coefficients. We will assume a vector autoregressive model of order P. We say it warp model. That means like we will assume the coefficients at time point t depends on the coefficients at the previous capital P time points by this matrix phi p, and we have again the residual terms cos t. We assume the residual term will follow a normal multivariate normal with covariance matrix U, and this U will be related to the covariance matrix K of this coefficients vector. And after the test, we assume that this phi p are diagonal matrices. So the covariance matrix U will inherit the sparse structure from K. And finally, in this step, we will store matrices phi p and capital U. So the sparse structure will save a lot of storage. So this is still for the annual case. But if we remember that when we like plot the histogram of the time series for the monthly and the daily data, we can see the skewness and heavy tails. So that means we need to Gaussianize the coefficients first, and then we can put this Gaussianized coefficients to this warp model. But how to like Gaussianize the coefficients? Here we use a Tukey G and H transformation. That's just a parametric function. Like here we have our coefficients at each index. And then we will use a function tau with parameters to Gaussianize the coefficients to this as chat. Then this will be Gaussian, and we put this Gaussianized ones to this warp model. Yeah, sure, please.
Thanks so much. It's very interesting. So stationarity in the geosciences has a different meaning. This is why the question came. So we use stationarity only in the temporal domain. And but I would be interested. So your basis function are spherical harmonics, so they're two-dimensional. And so now you're finding the coefficient, but you don't find the coefficient for the spherical, first spherical harmonic that's global. You somehow find a coefficient for each
Sorry?
So your spherical harmonics are global, two-dimensional.
Yeah.
But now because of the fact that you find a coefficient for each
No. It's for this SHT is actually for all the grid points, not by latitudes.
What is the point of the stationarity?
So like here. So if we fix at each latitude, we can assume stationarity. Yeah. So that means if we model the data on the same latitudes, the covariance will only depends on the distance. But we cannot to make it to across the latitudes. For example, if we cannot make that assumption because different latitudes show different spatial structures. Yeah, that's what I mean. Yeah. Thank you. Yeah, okay. So finally, let's summarize the modeling and the emulation process of our stochastic generator. So here, given the climate simulations, we will first model the deterministic component and remove them to get the stochastic component, and then we will do the SHT to transform the data in spatial domain to the spectral domain. And in the spectral domain, which means in a lower dimensional space, we will build a stochastic model for these coefficients. And use this stochastic model, we can generate new coefficients and use inverse SHT to transform them back to the spatial domain. And then we add the deterministic component back to get our emulation. That's the whole idea. And we will only need to store the model parameters instead of the climate output, instead of our emulation. Yeah. So let's see the performance of our stochastic generator. So here I just show the performance for the daily case. We will model the data at 5 years. And here are some selection of the tuning parameters in the model, like the terms, the numbers of the harmonic term in the deterministic component, the capital K, and the Q values for land and ocean, and the P values in our the VAR model. After we build this stochastic generator, we can generate the emulations, and we will assess the performance of the emulations by comparing them with the simulations. So here we choose 2 indices. The first one, the IUQ, actually measures the variability of the emulations. So we fix at each grid point, and we have the time series of the emulations and simulations, and we compare their variability. So the closer the value IUQ to 1, the better the performance. And another index is the Weierstrass distance, is the distribution similarity between the simulation and emulation. It's still at each grid point. Remember, we have the histogram. So it's actually, we compare the histogram of the emulations with that of simulations. So using the Weierstrass distance. So the smaller the value, the more close to 0, the better the performance. Okay, so here is our in plot A and C are our performance. Here we also compare our methods with another methods which model in the spatial domain directly. They also assume the axial symmetry. Like here you can see they model at each latitude, and they use autoregressive model to model the dependence between different latitudes. That's why their results looks discontinuous. But for our model, we just transform to the spectral domain and then model, so it's fine. This is the IUQ values. So the darker the color, both in red and blue, the worse the performance. And here is the Weierstrass distance. So we hope the color to be blue, and the more yellow, the more bad. So for most grid points, our methods performs well. But for these 2 regions, the North Pole region and this band region near the South Pole, our stochastic generators perform not that good. So to figure out what happened at these 2 regions, we choose 4 grid points. The first one is near the equator and unlined. The second one is at the mid-latitude on ocean. The third one is still mid-latitude ocean, but it's very close to this band region. The fourth one is within the band region. We directly compare the generated emulations of all ensembles with the shifted simulations. So at these 4 grid points, and the the green curves represent the emulations. The blue curves represent the shifted simulations. So at the first two grid points, where we can see the performance, the index are good. So we can see the performance are also good. The simulations and the emulations look similar. And for data online, they have higher uncertainty than the data on ocean. But if we look at the emulations and simulations at the third point, we can see because here the simulations have a sudden drop at this time point. So we overestimate the uncertainty of the data, and the emulations have higher uncertainty. And also for the grid point within this band region, the situation is worse. We have much instabilities and worse performance. So for this problem, I asked scientists in NCAR, and they told me because these two regions is just a mixed region of CS and C. So at this region, we have a dynamic transition between this CS and C. So sometimes we have surface temperature for the C. Sometimes we have that for the CS. That's why we can have these numerical instabilities. Okay, so finally, let's summarize our work. We built an efficient stochastic generator. It can generate even daily surface temperature emulations on a standard desktop computer. And we only need to store limited parameters, but we can generate unlimited number of emulations when we want to use. And they can be used as a practical complement to the CSM toolines too. And we can check more details in our paper. And based on this work, we have two extensions. The first one is with the support of the supercomputer, we further validate and test our method. We built an axial scale stochastic generator. And this work won the 2024 ACM Golden Bell Prize for climate modeling. And we can see Alison is in our team. And thank you for your help. And so why I say climate emulator here is because we think this word may be more familiar for data from for scientists from computing department. So that's why we use climate emulator. But actually, we build a stochastic generator. So this plot shows the breakthroughs of our actual scale climate emulator. So here the x-axis represents the spatial resolution in kilometer, and the y-axis represents log-scaled computational complexity scaling. So here the black box means the existing work. So we can see they only achieve this about 100 kilometers. And most of this existing climate emulator or stochastic generator, they assume the axial symmetry. That means, remember that our covariance matrix K have a sparse matrix. And actually after the reorder, we can have this block diagonal structure. So the contribution of the actual scale climate emulator or climate stochastic generator is that we can emulate data up to about 3.5 kilometer, and we can emulate data at hourly temporal resolution. And also, we use a full covariance matrix without the axial symmetry assumption, which means we didn't lose any elements here. That's our main contribution. Yes, so from the computational side, Our implementation applies multiple precisions, catering to the covariance strengths of the data. And we also relies on the parsec runtime system to support the efficient matrix operation, parallel matrix operations. The large-scale execution and performance demonstration on system equipped with 4 different GPU accelerators, the Frontier, Alps, Leonardo, and Summit. And we achieved good performance in the parallel computing. So I also want to show our the generated emulations. So actually in this work, we used the ERA5 data at 25 kilometer spatial resolution. It's still for the surface temperature data size. So we built stochastic generator for daily data spanning 83 years of size 31 billion, and also hourly data spanning 35 years of size 318 billion. So here, maybe you can show. No? Okay, sorry. So I will not show now, but how to go back to this? Yes. Yeah, sorry. Oh, sorry. Yeah, thank you. So we can't show our emulation, but we can see our emulation here. Can compare it with the simulations. So actually, they are statistically consistent with the simulation, and we also upscaled the simulation data to ultra high spatial resolution of 3.5 kilometers to test to see the scalability of our design, and we generate emulations at this spatial resolution and hourly temporal resolution of 1 year, and is of size about 477 billion. So this is one extension. Another extension is that we built an online regional stochastic generator. So in this work, we incorporate the online updating idea, which means we allow the data to sequentially enter the model in blocks of time and to update the parameters in the model. So in this way, we can reduce the storage demands during the modeling because we don't need to store all the data at the same time. We just allow them to enter by blocks. And another advantage is that we enable near real-time emulations. That if we have simulations that come in near real time, then we can generate emulations in this way. That's the advantages of the online updating. And also because now we focus on the regional data over the globe, so we cannot use the spherical harmonics. We use the Slepian basis. These bases are data independent, which means we can use this basis for all kinds of variables or other data. And they can optimally concentrated within this specific global region. So for example, the parameter lambda indicates how concentrated the Slepian bases are. And when lambda equals 1 for these several bases, we can see they are fully concentrated in our regions. But when lambda smaller than 1, we can see the basis is outside the region. And when lambda equals 0, you can see it just cover the other regions except for the region we give. That's the Slepian basis. Yeah, okay. So here are the reference. And thank you for your patience. Yeah.
Thank you so much for the great talk. I think the overhead speakers are turned on, so if anyone has a question, and we'll also look on Slido. If you're online, you can enter your question there.
And so CSM2 will have force changes in the natural variability. I guess in your words, maybe deterministic changes in the stochastic variability. Do you capture that by training your model at different times, or?
No, it's for all times.
Okay, so if you have like changes in ENSO variance, you would just have the ENSO variance of the whole simulation throughout, I guess, not changing over time. I guess it's kind of there in your CISL time series that there's like a whole lot of variability, and then the CISL has gone away at the later decades, and so the variability is different.
Yes, that's one point, is because here we assume the standard deviation is the same. So this actually is a drawback of our methods. It's a great point.
Okay.
Thank you.
Other questions?
Mine was along those similar lines. So if you go to slide 19, I noticed what Isla is pointing out is that in the bottom left, like when there's sea ice in 2020, or bottom right, 2040 and 2060, like you get a lot of variability, and that's when you're saying the emulation is not good. But then as you go further on, it looks like, there's no variability because the sea ice is all gone. So I know nothing about emulations. Like, what do you do in these regions where there's a huge force change or deterministic change, and it looks to me like the emulator kind of fails in those regions that I focus on in my research. So what are people doing, whether it's your group or others? Like, is there anything you can do there?
So for our model, because the model can somehow can stand with the outliers. So because we model on all the all the time points, so there are a lot of data. So if there are only one point that are not that good, then we can still model it well. But if at this case we cannot, because there are too many outliers.
Okay.
Your description of what you mean by stationarity is, you refer to it as the covariance between the output at two different locations only depends upon the distance. If I imagine, like in one latitude band, if I've got two grid points that are a fixed distance apart, if they're both on land versus both on ocean or land or ocean, I would not, from a physics point of view, expect them to have the same covariance.
Yeah, sure.
So, but it seems like if I'm interpreting, my understanding is you're saying that you're assuming that they do have the same covariance. So I'm a bit confused about my physical intuition versus what you're saying.
Yeah, thank you for your point. So it's different non-stationarity. So I also mentioned the non-stationarity among the land and ocean. So here we give different Q values. So if we take this into account, then we can see the difference if we calculate the covariance.
Well, to follow up on his point, if you just think physically about the North American continent and you take a latitude, if you look at two grid points that are, say, 50 kilometers apart. Now, if they are right near the front range of the Rockies, that's got to be different from out in the middle of the prairie regions, even though it's the same latitude, even though it's just on land. So I think that people who think more physically have trouble absorbing the value of this assumption. Do you understand?
Yeah, I understand. It depends on the physics. But one point is that the resolution of this data size is about 100 kilometers, so it's not that.
Well, even if you take 100 kilometers and you move your 100-kilometer stretch back and forth across the 40th latitude, we're just about there, you get a very different answer if you're in Boulder and you're thinking about well west of the Rockies, or Chicago, and some point, that variability must be different, even though the distance is the same.
Can we pause a minute? Are there any on Slido, Kelvin? No, they're not. Okay, go ahead.
So, great talk, and I'm really interested in what you're doing. But I'm wondering about the metrics you're using to say whether the emulator's working. So if you just get the right distribution of statistics, but you've not got process understanding, you've got no ability to actually use that model to inform you of what's happening in the planet. You just say, okay, at this point we now get a nice distribution of statistics. Is that a success of the emulator? Or is that just one component of what you'd really care
One
about?
component is we need a lot of assessments, but for now we just use this tool.
Right, but I'm just sort of saying, like, to evaluate whether it's working or not. Just because you get the right sort of kurtosis and the right skew, does that really tell you anything about how well you've captured the nature of the emulation you've done?
Yeah, so it depends on what we want. So if we want to model this uncertainty while, then we just compare the uncertainty. If you want other characteristics, then you use other assessment methods. It depends on what we want from this emulation.
I guess it comes back to the whole idea of using one latitude and band to say, at this point, depending on how far you're on the latitude band, this is the interannual variability you would get. I'm just wondering how well that assesses the ability to use the model, the emulation you're using. For lots of different applications.
So for now, we didn't use emulations to other applications, just to compare it with the simulations we use. And if they are statistically consistent, then we say it performs well.
So to maybe give a suggestion to that, folks next to me here at NCAR have developed a package to look at really key metrics of climate simulations that climate scientists care about, that you could just run through all your simulations and see like how do really key physical indices compare between your emulator and the model. That'd be a relatively easy way to check.
Maybe last questions?
There's another question about if you were to generate a 1,000,000-member ensemble with your emulator and compare the distribution of global average surface temperature or something to the actual large ensemble, would you expect the variance in your much, much larger ensemble to be larger than the variance within the large ensemble that was trained on?
The number of ensembles should be the same when we compare them, or it will be different.
I guess what I'm asking is, do you expect to ever get a realization from your emulator that's outside the range of the training data?
Outside range, you mean outside for the 10 points or what?
For any metric?
For any metric, then I think it will be fine. If it's interpolation, I think it will be fine. But our target is not to predict at some point or something. So it's just to like generate new data at the previous point, like the grid point we have and the 10 point we have. So it's kind of different from the prediction or forecast. It's not like this.
Okay, well, thank you. Last I checked, there was still one slot open if anyone wants to meet with Jan this afternoon, and we'll also be in the cafeteria